Dr. Williams again. So we're going to look at chemistry today. This is chemistry paper 1, the C4 unit on chemical changes. Okay, let's get started then. So some of this knowledge actually relies on you understanding what happened in C1 and C2, and more importantly, what an ion is. So it's really important that you recognise that when metals react with other substances, they have to form positive ions. And that's what makes them reactive. So as you can see, there's sodium, and if sodium loses one of its electrons on its outer shell, then it has a full outer shell and becomes a positively charged ion. Magnesium has 2 electrons on its outer shell because it's in group 2, so that will lose 2 electrons. Therefore, the full outer shell is in the ion, means it's got a positive 2+ charge. So all metals form positive ions, and their ease of doing this determines how reactive they are. And when we look at the metals, we can arrange them in their order of reactivity. You start at the top with the most reactive, and they're going to be your alkali metals, and calcium's up there as well. And as you work down to the bottom, you get the least reactive, and they're usually precious metals like gold and platinum and silver. And if we rank all the metals, we can rank them all in order like this, and this is called the reactivity series. We also put 2 non-metals in the reactivity series to show how reactive the metals are compared to those. This can be really useful when we look at how to extract metals using electrolysis or reduction. When metals actually react with oxygen, they produce metal oxides, and obviously those near the top of the reactivity series will do this more easily than those at the bottom. When a metal reacts with oxygen, it's called an oxidation reaction because the metals gain oxygen. And there's 2 examples just there. Magnesium plus oxygen reacts to make magnesium oxide. And you can see the symbol equation below, which is balanced. So we need 2 atoms of magnesium to react with 1 molecule of oxygen to make magnesium oxide. And you can see also the state symbols. So S meaning solid and G meaning gas. And also iron. Iron and oxygen react to make iron oxide. There's the balanced symbol equation underneath. And you can see a photograph of some rusty iron nails. The rust is actually the iron oxide. Metals are also going to react with water. The more reactive metals like potassium, sodium and calcium react with water to produce a metal hydroxide, which is an alkali, and hydrogen gas. There you can see the general word equation for a metal reaction with water. We have metal plus water react to make metal hydroxide and hydrogen. And the alkali metals are very reactive with water, and you'll learn about that in C1. But here are some of those metals that you can see there in a diagram of how vigorously they can react with water. So potassium, when it reacts with water, makes potassium hydroxide and hydrogen, and the hydrogen gas that it gives off fizzes around, and it's an exothermic reaction, so that hydrogen gas can actually set on fire as well. Sodium is a bit less reactive than potassium, and there you can see the word and the symbol equation for the reaction of sodium with water. And calcium, which is in group 2, also reacts with water, less vigorously than the group 1 metals shown there. And you can see again the word and the balanced symbol equation for those. Here you can see there's other state symbols of AQ, which means aqueous, and that means that the potassium hydroxide is dissolved in a water solution, and the G meaning gas, L meaning liquid, so the liquid is in the pure form, so that's just pure water would mean a liquid, and S, which means solid. Metals like magnesium, zinc and iron also react with acids to produce salt and hydrogen gas. In fact, lots of metals will react with acids. Those alkali metals will, but it's far too dangerous to do that, especially in a laboratory, because they are so reactive. So we often react to things like magnesium and zinc and iron with acid in our laboratories. And there you can see the word equation for those is a metal plus acid react to make salt and hydrogen. So we call them MASH reactions, and that's the general word equation. If we look at specific examples of magnesium reacting with hydrochloric acid, you can say it makes the salt called magnesium chloride. Zinc, if you react it with hydrochloric acid, makes the salt zinc chloride, and iron with hydrochloric acid makes the salt iron chloride. If you use a different acid, though, the name of the salt will also change. So the name of the salts produced in reactions with a metal or even a metal compound will depend on which acid you're going to use to react with the metal part. So metal and hydrochloric acid always make metal chloride salts. If you put a metal with sulfuric acid, you make metal sulfate. And if that metal is pure metal, you would also produce hydrogen. Metal plus nitric acid makes metal nitrate and hydrogen. So you can see hydrochloric acid, the formula for that is HCl, which hopefully you should know. The formula for sulfuric acid is H2SO4, which again you should know. And the formula for nitric acid is HNO3, which you should also know. So you need to be familiar with the three acids and those three salts that they make when you're reacting with metals or metal compounds. When looking at reactivity of metals, you can also think about displacement reactions. And a displacement reaction is when a more reactive metal displaces or takes the place of a less reactive metal in its compound. So for example there, magnesium, if you look at the reactivity series in the right-hand corner, you see magnesium is higher up than copper. That means it's more reactive than copper. So if you put magnesium and in a copper sulfate solution, the magnesium will take the place of the copper. That will form magnesium sulfate, and the copper will be left on its own. So you can see the symbol equation underneath there as well. So that's a displacement reactions. And really that's happening because of the transfer of electrons. So the more reactive metal is losing electrons. So in that case, that would be magnesium is losing electrons. And the magnesium, when it loses electrons, becomes oxidized. The less reactive metal gains electrons. So we say that one is reduced. Now we can use ideas of reactivity to help us understand how to extract metals. Unreactive metals, such as gold, are found in the earth as pure metal itself. But most metals are found as compounds, and they'll require chemical reactions to extract them. Metals are often found in the earth's crust as ores, and an ore is just a rock containing enough metal to make it worth extracting. So there you can see an ore of aluminium, which we call bauxite. You can see it's a rock, but we know that there's some aluminium in there that we can extract. When we want to extract metals, the cheapest way to do that and the easiest way is to use reduction. But you can only use this with metals which are less reactive than carbon. For example, iron and zinc. And they can be extracted from their ores using carbon in a reduction reaction. So this often involves a furnace, as you can see the diagram there, which you have to heat up. And you put your ore in with some carbon, and what you should be able to extract is the pure metal from that ore. This is because reduction involves the loss of oxygen. Now for the higher tier, you need to understand reduction of metals in a bit more detail. You need to know that oxidation is the loss of electrons and reduction is the gain of electrons, and that these reactions are called redox reactions. So oxidation being loss of electron, reduction being gain. You can remember oil rig as a way to help you remember that. So oil rig stands for oxidation is loss, reduction is gain. And there you can see an example of magnesium and copper and sulfate forming magnesium and sulfate and copper. And you notice that some are ions and they're changing to atoms. If we take the sulfur away, we can see what's happening here with magnesium and copper. And you can see that the magnesium has lost electrons and the copper has gained them. So what that means, if we look at the ionic equations to actually be able to track where those electrons have gone, is that the solid magnesium has actually formed a magnesium ion and lost 2 electrons. So as it's lost 2 electrons, it's an oxidation reaction. And if we look at copper, it's gained 2 electrons and become copper atoms. So that's a reduction reaction. And you could represent redox reactions with ionic equations. You show the electron as an E minus, and just like balancing normal equations, you would put the numbers of electrons that you gain or lose in front of the E minus sign. So in terms of reactions of metals, we can also start to look at different types of reactions. And another reaction we can look at is neutralization reactions. And neutralization reactions involve acids and alkalis or bases. So acids can be neutralized by alkalis, and alkali is just a soluble metal hydroxide, and bases are insoluble metal hydroxides or metal oxides. And when a neutralization reaction happens, when an acid is neutralized by an alkali, you form salt and water. And there you can see the general reaction is acid plus your base or alkali react to make salt and water. And there's an example with hydrochloric acid and sodium hydroxide, and you actually make the salt, sodium chloride, and water. The name of the salt is similar to before. The salt formed in reactions depends on the positive ions, in other words, the metals which are in your base or your alkali, or even a carbonate, and the acid used. Hydrochloric acid produces chlorides, sulfuric acid produces sulfates, and nitric acid produces nitrates. Exactly the same as before when we looked at the metal and acid reaction. The required practical involving these ideas is about making a soluble salt. So if we use the idea of acid and base reactions, we can make a soluble salt by getting an acid to react with a solid, insoluble substance. That could be a metal oxide, a metal hydroxide, or carbonate, as long as it's insoluble and will react with the acid. The solid is added to the acid until no more reacts, and the excess solid is then filtered off, and this produces a solution of the salt. This salt solution can then be crystallized to produce a solid soluble salt. So it might be that you are asked to write a method for this. If you are, it will be specific about the type of acid you need to make and the type of base that you need to use, because it will ask you to make a certain type of salt. For example, magnesium sulfate. So in that case, you would react your solid metal, maybe magnesium, with sulfuric acid. And you would filter off any unreacted magnesium, and then you would crystallize the salt solution, and magnesium sulfate would be left behind. So those key steps can make any soluble salt. You just have to be careful about which acid and which metal or metal carbonate, oxide or hydroxide you're going to use to make your salt. You'll be familiar with the pH scale from Key Stage 3, but you need to understand it again for this unit. The pH scale measures how acidic or alkaline a solution is, and it ranges from 0, which is acidic, to 14, which is alkali. 7 is neutral. And we can use indicators for the pH scale to show us what the pH of a solution is. The red colour with the universal indicator indicates acidic solutions. Neutral in universal indicator is in the middle, and alkaline solutions are more purple. There are other indicators, for example, litmus paper, which just changes one colour. So just whatever indicator it talks to you about, you should understand what universal indicator is, or be able to use any indicator an exam question will ask you about. Any substances that are less than pH 7 are acidic, and the reason is because acids have hydrogen ions in them. A hydrogen ion is H+, so it's basically lost an electron. And that happens when those acids are in a solution of water. Substances with a pH greater than 7 produce hydroxide ions in aqueous solutions. So you can see you've got substances anywhere which are 10, 11, 12, 13 and 14 can do this to a high amount and make lots of hydroxide ions. In the middle, neutral solutions, they have hydrogen ions and hydroxide ions in equal amounts, which is why they are neutral solutions. When an acid reacts with an alkali, the hydrogen ions from the acid react with the hydroxide ions from the alkali, and that actually forms water, and that is the neutralization reaction. So there is an example of that equation below, where you can see a hydrogen ion plus a hydroxide ion forming water. If you're doing the higher tier, you need to know a bit more about the pH. A strong acid is going to be completely ionized to form hydrogen ions in an aqueous solution. For example, the ionization of hydrochloric acid. That's what makes them acidic. So hydrochloric acid will strongly ionize, so it will have lots of hydrogen ions formed. And it will also form chlorine ions when you put it in a solution. A weak acid is only partially ionized in aqueous solution. And examples of weak acids are ethanoic, citric, and carbonic acids. When you've got an aqueous solution, the stronger the acid, the lower the pH. And each pH unit is actually a decrease of hydrogen ion concentration by a factor of 10. So if we could measure the hydrogen ion concentration, it changes by a factor of 10 each time we move down the pH scale. Now, the last sort of section which uses all of this knowledge together is about electrolysis. And electrolysis is the process that uses electricity to break down ionic compounds, which are basically a metal or a non-metal, into their elements. And there are different ways that we can do this. When an ionic compound is melted or dissolved in water, the ions are free to move about. That's because they are now able to carry charge in the liquid because they've been melted, or the solution if they're in water. These liquids and solutions are able to conduct electricity because they carry charges, and they are called electrolytes. If we pass a current through the electrolytes, this causes the ions to move to the electrodes, and therefore we can actually make a circuit. If you look at the electrolysis equipment, what we need are two electrodes, which are basically pieces of metal that we'll put into our solution or molten ionic compound. And one of those electrodes is positive, and one of those electrodes is negative. So when we connect it to a power supply, if there are ions which are free to move in the solution, then they will move towards the either positive or negative electrode, depending on their charges. So positive electrodes attract negative ions, negative electrodes attract positive ions. Electrodes are often made from an inert or unreactive material, such as graphite or carbon. This is so they don't react with the ions in the electrolyte. Here's an example of electrolysis of molten ionic compounds. For this, we need to use our ideas of oil rig, that oxidation is loss and reduction is gain of electrons. And we need to think about the actual charges that are able to move. So when a simple ionic compound, such as lead bromide, and remember lead bromide, the lead is the metal, the bromine is the non-metal, but it's in an ionic compound, so it'll have charges. What we have to do is we have to melt it and make it become in the molten state, so those charged ions are able to move. So lead bromide is electrolyzed in the molten state. The metal is produced at the negative electrode, and the non-metal is produced at the positive electrode. The positive metal ions at the negative electrode gain electrons and are reduced, and this discharges the metal. This makes the metal come out of the molten lead bromide, while negative non-metal ions at the positive electrode become oxidized. Let's have a little look in more detail at what is actually happening here. So if we could see those ions in that solution, what it would look like is something like this. We've got molten lead bromide in our solution, and there you can see a lead bromide together, so it's just about melting. So you have to heat it to make sure that it's molten and those ions are free to move. When you've heated it, as soon as you switch on the power supply, a current will flow, and they'll flow through the wires and they'll head towards the negative electrode. So you can see these electrons here, which is your current, and they will head towards the negative electrode. That's often made of something like graphite because it's inert and shouldn't react with those ions in that molten lead bromide. What happens is when you've got those negative electrons there, you will get the positively charged lead ions attracted towards the negative electrode. That's due to their electrostatic forces. And then at the negative electrode, when the positive lead ion has moved towards it, because it's positive, it will actually attract the electrodes onto that ion itself. So that will form lead. And lead as an atom will then start, we say, is discharged. You will start to see lead appear at that electrode. If you're doing the higher tier, you need to be able to show that in terms of an ionic equation. So there you can see the lead ion gaining 2 electrons to become lead. The reason it gains 2 electrons is because lead ions have a charge of 2 plus. While that's going on at the negative electrode, we also need to think about what's happening at the positive electrode. We can only have a current if there is a flow of charge, and this is how the flow of charge really happens. So while the positive ions are going towards the negative electrode, the negatively charged bromide ions move towards the positive electrode, again due to their electrostatic forces of attraction. And then here you can see when the bromide ions are actually at the positive electrode, they lose an electron. So that electron that they were carrying, the extra electron, is lost. And when the bromide ions have lost their electron, they actually join together in a covalent bond to form bromine. So bromine, remember, is a small molecule with a covalent bond inside of it. Bromine gas is then discharged at that electrode. Again, if you're doing the higher tier, you'll need to know that 2 bromide ions are losing electrons to form bromine, and you can show that as 2Br minus going to Br2 plus 2E minus. So they're losing 2 electrons overall, and losing 1 electron from each bromide ion. If you look at that overall, then this all obviously is going to happen at the same time. What you need to do is melt the compound. In this case, it's lead bromide, so the ions are free to move. Then you apply your current. The lead will move towards the negative electrode and gain 2 electrons and become reduced. And again, if you need to know that ionic equation, make sure you know that. The bromine loses an electron at the positive electrode and actually turns into bromine gas and is discharged. So if we think about using electrolysis to actually extract metals, well, then we could go back to thinking about those ores. So metals can be extracted from molten compounds using electrolysis. And the reason that you'd use electrolysis is if your metal is too reactive to be extracted by reduction with carbon, or if the metal reacts with carbon itself. So if you look at the reactivity series, any metals above carbon would be suitable for electrolysis, as long as they don't react with carbon itself. Any metals below carbon would be much more suitable for reduction. And the reason you'd rather do reduction than electrolysis is because actually doing electrolysis requires lots of amount of energy. So you need to melt the compounds if you're making them, or make them suitable for extraction, and then make an electrical current. And so overall, with that whole process, it's a lot of energy and can cost a lot of money. However, it is worth doing to get some reactive metals from their ores. So let's look at aluminium ore again. Aluminium is manufactured by the electrolysis of a molten mixture of aluminium oxide. Aluminium oxide has got another name of bauxite. You also need to put cryolite in and use carbon as the positive electrode. Aluminium oxide is actually, first of all, dissolved in molten cryolite. And there you can see solid cryolite. Molten cryolite is melted cryolite, which actually just helps to lower the melting point of aluminium oxide. Then you can carry out electrolysis. So here's an example, a diagram, again, where we can see those ions and atoms and what happens in electrolysis of aluminium oxide. So the formula for aluminium oxide is Al2O3. And the first thing you need to do is melt the aluminium oxide or bauxite with the cryolite, which helps to lower the overall melting temperature of aluminium oxide. So the ions are then free to move and you can apply a current. The aluminium this time is our positive positive ion, and that positive ion will go towards the negative electrode. At the negative electrode, because aluminium ions have a charge of 3 plus, it will gain 3 electrons and form an aluminium atom. And there you will start to see the aluminium metal appear. At the positive electrode, you would get the oxygens with their negative charge move towards the positive electrode. They will then give their electrons to the positive electrode, and then that will continue on the circuit. And as they do that, the oxygen ions, as they form oxygen, will react with some of the carbon that actually the positive electrode is made from. So they don't produce oxygen gas, they actually produce carbon dioxide gas. This means that in electrolysis of aluminium oxide, you need to keep replacing the positive electrodes because the carbon actually will react with the oxygen and it will wear away the carbon in the positive electrode. Again, if you're doing higher, you need to know those ionic equations. So we have aluminium, which is an aluminium 3 plus ion, and it will gain 3 electrons at the negative electrode to form aluminium. And the reaction at the positive electrode is there are 2 oxygen ions, and they will form oxygen gas and 2 electrodes. It's actually the oxygen that's formed there that will then go on to react with carbon. So that is still the ionic equation of what's happening at the positive electrode, but the oxygen formed will react with carbon. Electrolysis doesn't need to just be used for extracting metals, it can be also used in electroplating. And electroplating is a process where you get a thin layer of metal deposited onto another object, and it uses electrolysis. The main reason you'd use this is for coating cheaper metals with more expensive ones, and that improves their appearance and protects against corrosion. All you do is you put the object to be plated and use it as your negative electrode, and the plating metal is the positive electrode. If the electrolyte solution contains ions of the plating metal, what you will see is the object, which is the negative electrode, will become coated in whatever the positive electrode metal is. And you can also use electrolysis in aqueous solutions. If an aqueous solution, remember, has hydrogen and hydroxide ions, and this happens because aqueous solutions, water, we know, has hydrogen and hydroxide ions in them. That means they will get involved in being attracted towards the negative and positive electrodes. So what that means is that hydrogen and oxygen can be produced at these electrodes as well as any metal or non-metal that might be dissolved in that solution. So at the negative electrode, we might get the metal or at the negative electrode, we'll get the metal appearing, but you'll also get hydrogen there, and from the water. So the hydrogen ions gain 2 electrons to form hydrogen gas. At the positive electrode, because there's hydroxide ions in the water, you'll have hydroxide ions actually losing 4 of their electrons. They'll form oxygen, and they'll also form water. So these need to be considered whenever you're looking at an ionic compound dissolved in a solution. So when we think about electrolyzing anything in an aqueous solution, we've also got to consider hydrogen and hydroxide ions. And the ions discharged when an aqueous solution is electrolyzed using inert electrodes depends on the relative reactivity of all the elements involved in the solution that you're using electrolysis on. So if you're considering the negative electrode, you would get hydrogen produced if the metal is more reactive than hydrogen. So if you're putting any of those metals above hydrogen, if any of those are present in your solution, then because they are more reactive with hydrogen, if they are in a water solution, hydrogen will be produced at the negative electrode. At the positive electrode, oxygen is produced. However, there's an exception to this. If your solution contains halide ions, that's anything in group 7, then the halogen is produced. So as a summary, if you're doing electrolysis of dissolved ionic compounds, if there are any positive metal ions in your solution, then they would be attracted to the negative electrode. But if the metal is more reactive than hydrogen, then the metal will not gain electrons and hydrogen will. So hydrogen will be discharged or released. If the metal is less reactive than hydrogen, for example, copper or silver or gold or platinum, the metal will gain electrons and that will be discharged or released in the solution. In terms of what's going on with the negative non-metal ions, if they're attracted to the positive electrode, then if the solution contains halide ions, and that is either chloride or bromide or iodide ions, then the halide ions will be discharged and released as halogens, chlorine, bromine, or iodine. If the solution doesn't have any halide ions in, then at the positive electrode, there will be oxygen discharged due to the oxide ions in the water. So that is a C4. There's quite a lot in there and it's quite complex at times. And there's always questions on electrolysis. So what I suggest you do now is watch certain bits of the video back to see that you still understand it, and then go and practice some exam questions just to check your understanding. If you're doing any tests or exams, then good luck, and I hope that helped.